So, in the last lecture we had studied the algorithm graph plan, and today we will see that with slight modifications to the style in which graph plan works, we can convert the planning problem into a Boolean satisfiability problem and solve it using SAT solvers. The reason why people wanted to why SATPlan was born was that there were a lot of new SAT solvers which could handle very large satisfiability problem instances and could solve them very quickly. So, to harness the power of this kind of SAT solvers, we can actually translate problems into SAT problems and solve them with SAT solvers, which was previously not practical because of the inherent complexity of SAT. So, the inherent complexity of SAT is still the same, it is still NP complete, but what people have found out is that many problems, many instances can be solved very efficiently, and in practice the instances which are very hard to solve do not appear very commonly. So, let us quickly trace back to what we had seen in the last class. We had just a minute, yeah. We had seen planning graphs, which was simply unfolding the state space tree of the planning problem level by level, right. And we had seen that because the set of mutexes decrease with monotonically decrease with every iteration, and also the set of literals monotonically increase through the iteration. So, this planning graph is finite and tapers off after some time, right. So, the first thing that we are going to try in SATPlan is to do this unfolding, but by producing SAT clauses, so that we have a SAT instance at every time step. So, what we are going to do is we are going to start with the initial state, which will be a set of clauses. Then we will create the set of clauses by applying one set of the axioms, right, and then the new set of clauses will be checked against the goal for satisfiability. So, I will explain with an example. So, it is the same planning graph that will get unfolded, but as SAT instances, right. But in addition to the basic set of clauses that are generated, we will also have to model the mutex actions, because all the set of clauses will not be in a conjunction. So, there will be disjunction between clauses. So, all these different kinds of mutex relations that we studied, namely inconsistent effects, interference and competing needs, all these will be modeled as SAT instances, right. Now, one thing that we must understand is that manually writing down an enormous number of clauses is not possible. So, the front end of the planner will have to be something which allows us to succinctly express many clauses, maybe in form of first order kind of predicates with for all x, etc. And then internally the planner will expand out that first order clause in terms of propositional clauses. So, suppose we have for all the domain of x and generate PA, PB, PC like that, right. So, internally it will solve a Boolean satisfiability problem, but the front end can be different, as we shall see. Then similarly for mutex literals also we will have to adopt the same kind of approach. Okay. Let us skip through this. Right. So, essentially what we are trying to do is to translate the planning problem into a CNF satisfiability problem. The goal is asserted to hold at a time step t, and clauses are included for each time step up to t. So, what we will do is initially we will assume t equal to 0, and then try to see whether the goal can be asserted by generating clauses only up to the first time step, which means that the initial set of facts, whether they can actually imply the goal. Then we will increase time, if not, then we will increase time step by 1, right. So, at I am trying to see whether within k time steps I am able to satisfy the goal. If so, then there is a plan of length k, right. If the clauses are satisfiable, then a plan is extracted by examining the actions that are true, right. Otherwise, we increment t and repeat. So, this is the basic. Let us take an example and elaborate on this. So, suppose we have the following Bloch's world problem. Bloch's world is a very famous example of planning problems, where we have different blocks, like this is A, this is B, and they are all on a table. So, this is a classical, this Bloch's world is a classical world for representing planning problems and has been used in variety of domains like robotics, etc. So, the idea is that we have a set of blocks. Here I have just 2 for this example, but you can have any k number of blocks, and they are on the table in different configurations. So, you can have A on top of B and C on top of D, and then you can have another block here with some other things on top of it, right. And then, so that is a starting configuration, and then you have to reach an ending configuration. So, suppose I have something like A, B, C, and then D, E, F, and then maybe the configuration that I want to reach at the end is C on top of B, then I have F, E, A on top of it, and maybe D lying here. So, this is the initial, this is the final, and the planning is will tell me the sequence of actions that I can do. What are the actions that I have? I can move which moves now there is a precondition of this. There is a precondition of this action, and the precondition is that the top of y, that there should be nothing else on top of y, right, and also there can be nothing on top of x. So, you can move only one block at a time. You cannot pick up D and E together and move it to some other place, right. You can pick up only the topmost block of every stack and move it either on top of any of the other blocks, or you can put it on the table. So, this is a set of rules, and the set of predicates are things like on B A, indicating that B is A is on right, and we also have a special predicate called on table C, which says that C is on the table, right. So, this is a glimpse of the Bloch's world. So, in the Bloch's world, the planning problem will use this sequence of actions and translate the initial state to the final state. Now, let us see what kind of how can we model this Bloch's world problem as SAT problems. So, to examine this, I will start with one example where the initial state is A, this is the initial state, and finally I will require that A is on the table and B is on top of A. Okay, that will be my goal. Now, let us see how do we model the initial state as a set of clauses. So, we will write on table B, and I will put a 0 here to indicate that this is in the time step 0, and I will have on B A. Is that sufficient?
There is nothing on top of it.
Yes.
That should also be there.
Yes, but if there is nothing, then you cannot specify that. What is not on top of A you cannot specify, but there are other things that we must specify, because see, in our in the connotation of planning that we have in this world, we know that if B is on the table, then B cannot be on top of A, right, and also we know that if A is on top of B, then A cannot be on the table. So, we must add clauses like not on table, A, and not on Now, see, these things should come by default, but when we actually model it in propositional satisfiability, then we have to explicitly create these clauses. Otherwise, for another domain, this is not automatic, right, and CNF SAT does not know which domain you are talking about, it just treats them as a set of propositional clauses. So, we have to add these things. Then yes.
Don't we have to specify that there are just two blocks, nothing is above A?
If see that is going to come automatically by the propositional satisfiability. For example, if you have a CNF formula which is on variables x1, x2, x3, right, then the variable x4 which does not exist in the formula is automatically taken care of. So, if there is any variable which does not appear at all in the formula, then that is fine, we do not have to worry about that. But if there are some variables which are there in the formula, then we must exactly specify the initial state, otherwise it will represent possible inconsistencies in the domain, like having two blocks on top of the same block kind of thing. Later we will see how we can express those general axioms also in the SATPlan scenario, so that explicitly we do not have to write many things. But I am saying that these clauses will anyway have to be generated internally, whether we specify it externally or not, they will have to be generated internally for this domain. Then we will have a bunch of successor state axioms, which are going to tell us that if we have this set of clauses, then what are the things that we can deduce from it, right. So, these will actually indicate the effect of the different actions. So, suppose we write that on AB in time step 1, and then we will have to write as if and only if how we can achieve this, right. So, this is the effect that we want, and then here we have to enumerate all the different ways of achieving this. So, let us see what are the different ways of achieving that. One way of achieving this is you have on table B in the 0th time step, and you have right, and the action is this is one way of achieving this. So, in the 0th time step B was on the table, A was on the table, and we moved B to the top of A. This is one way of achieving it. Okay. Then or another way of achieving this is we already had on A B in time step 0, and we have the persistence of that. How do we indicate the persistence? We say that don't move B away from top of A. So, not of move right. And so on, you have to enumerate all the other ways of achieving this, right. Let us say that so far we just add these two. Okay. Then what? Yes.
So, why do we have the time step 0 on the right hand side?
Okay. What we are saying is that if we have these clauses at time step 0, then in time step 1 we will have this. These successor state axioms will generalize for k, the kth time step here and the k plus 1th time step here, right. So, in general we will have this as k and this as k plus 1. But yes.
So in that step, is it move B comma table or A comma table? B will not move.
B. See, this says that you already have B on A, and you do not move B. Then you will still have B on A in time step 1. So, this says that you already had B on A and you do not move it, then in the next time step also you will have B on A. Right. Now, the successor state axioms can be.
Do we have to write not on of A, B, comma A, sir?
Not
Not on of
for this,
A, sir?
yes, we have to. In fact, we will see later on that we will add some other actions, general rules, which will always generate the clauses that whenever B is on A, then A cannot be on B, right. So, those are the additional. So, I am trying to show you that there is a lot of additional work that goes into generating the clauses. So, here for example, when we have this in general we will express this successor state axioms in terms of what we can have in the k plus 1th time step in terms of what we have in the kth time step or previous less than k time steps, right. But when we actually want to apply this axiom by on the SATPlan instance, then when initially we are in time step 0, we will check what we can generate in time step 1. When we are in time step 2, we will see what we can generate in time step 3 and so on, right. So, this value of k and k plus 1 will get instantiated as we progress down the iterations. After doing this, after generating the set of successor state axioms and the initial state propositions that are given to us, we will check for the satisfiability of the following thing. we will also represent the goal as a set of clauses, which means that we will check say on table A and on A B, right. This is our goal. So, what we will try initially, we will try to solve this problem in one time step. So, we will say that okay, t is 1. So, if t is 1, then in the we will expect that these goal clauses will be reduced in time step 1. So, we will have them as time step 1, right, and then we will see that whether we can AND this with the initial state, right, and with the successor state axioms, and then we will check for this whole thing whether it is whether it is satisfiable, right. So, if this is satisfiable, then there is an assignment of values to the axioms such that we are able to reduce the goal. Now, is that clear to you? What is it that the SAT is trying to assign? What is it that the SAT is trying to solve? It is trying to tell us that which of these successor state axioms we require, so that we are able to deduce these, right. So, we take the initial state, we take the set of successor state axioms, and we take the set of goal propositions, AND them together and check for satisfiability. Now, if this is unsatisfiable, then we clearly do not have a plan yet. So, we have to increase t to 2 and proceed forward, right, and again generate all the clauses up to time step 2, create a similar SAT instance like this, and again check for satisfiability. This is how SATPlan will work, but there are a lot of other things that we need to do. For example, there are certain actions which will require preconditions. Let me give an example. So, we will require things like and an example of this could be that when we have move in some time step 0, then it implies so what does this say? That suppose you want to move B on top of A. So, this action can be true only, I mean provided that on B A is not true. So, what does on B A mean? That we have A on top of B, right. If this is true, then obviously you cannot move B on top of A, right. So, this is a precondition of the action. So, for every action there will be a set of preconditions, right.
So, precondition should be in the time step before the action is being done.
No, see what we recall how we were in graph plan. Do you remember that we had the state S0, which was a set of propositions, and then A0 is the set of actions that were taken over that set of propositions. So, our indexes indicate that this is the set of actions which are taken on the initial set. Then that gives us S1, and then the actions that are applicable on S1 are given by A1, right. So, similarly that is why we have this and this. So, if we have this in 0, then this action can be applicable on the initial state. Right. It is just a matter of putting the nomenclature of defining these index terms, right. But you are right that once we have the knot of this, only then we can apply this action.
So, also if all of AB is true, then this thing is not possible, sir. If say you true all AB, then say since B is on top of B, we cannot move A on top of B, sir, directly.
If you have on
A comma B,
on A comma B means B is on A.
Yes, sir. In that case, we cannot move A on top of B directly, sir.
No, this means move B to top of A.
Yes, sir.
Yes.
In that case, not possible to do move B comma A, sir.
Because it is already on top.
Yes, sir. In that case also, sir.
No, in that case it can be true also, there is no problem. You can just pick it up and put it down back there, right. No, but the condition that, see, I think you are confused. What you are saying is what we have written here. This says move B to top of A, right. So, right. So, we have just written what you are saying is exactly what we have written here. So, you have A on top of B, so you cannot move B to top of A. That is what you wanted to say, right. Okay. So, in addition to this, there will be a bunch of other things also, like we will have action exclusion axioms. Now, this basically tells us which actions are mutex. So, for example, you can let me write down one action exclusion axiom. So, I have move B A and now let us see what this says. This says move B to the top of A and in the same time step move B to table, right. Now, we can't move the same thing to two different places in the same time step. So, therefore, these we have to explicitly specify that these two cannot happen together. So, the action exclusion axiom will say that not of this. In other words, that these two actions are mutex, you cannot do both of them, right. So, for all pairs of mutex actions, we have to add exclusion axioms like this, which says that if you have this, you cannot have this, and so on. And then recall that we also had exclusion between the literals in a state. So, how do we express that kind of mutex? So, those will be called as state constraints. So, for example, we want to express the fact that two blocks which means that this is not allowed. This is not allowed. All blocks are of the same size, we cannot allow this, right. So, how do we express this? So, we can express this in a kind of first order form, where we say for all p x y t, x not equal to y implies so we have, what does this say, that suppose in a given time step t we have x on p and we also have y on p. This is not allowed. So, we have not of this and for all p x y t, but we also have to put this x not equal to y, because both of these x and y can get instantiated to the same block. So, this is a typical state constraint, right. So, in our planning problem what we need to do is to represent the initial set of states, the set of clauses for the initial state, then the precondition axioms, the action exclusion axioms and the state constraints, and then progressively increase the time step and check whether we are able to satisfy the set of goal constraints. So, this is the SATPlan algorithm. So, we need a T max. Now, see, this is where we have to be careful, that SATPlan requires a bound on the number of time steps within which you expect to find a solution, right. So, for t equal to 0 to t max, do the CNF comma mapping is translate to SAT problem t. So, what we are effectively doing is we are generating all the clauses up to time step t, right, and then we are calling the SAT solver with the CNF that we have found by this translation. So, if it finds that the assignment is null, then we still do not have a solution, it is not satisfiable. If it is not null, then we do have a satisfying assignment, then we call the extract solution from the assignment mapping. Effectively what happens is, we see each of our move actions, they are also predicates, like when we have this text please, text please, text please, we have this, see these move actions, these all have these are all also predicates, right. So, if we assign true to this predicate, it means that we are actually applying this action. So, at the end of the satisfiability, we check which of these actions have been given the true value, right, and that is the set of actions that are part of the plan. Okay. So, once we have the assignment, then we can extract the solution by checking which of the actions have been assigned 1, right. Otherwise, we return failure. If we are still unable to find a satisfaction within T max, we return failure. Now, the question is, what value of T max should we use? How should we decide the value of T max? what could be the maximum that T max can take place? Okay. Recall that we had seen that the planning graph when unfolded will taper off after finite number of steps, right. So, if we could somehow gauge the diameter of the planning graph, then we can give an accurate T max, within which we should be getting this thing, right. So, again there has been research on the fundamental problem of determining the diameter of a graph which is specified implicitly. So, the graph is not given to you as the entire set of nodes and etc. What is given to you is the initial state and a set of state transition relations, right. And without unfolding the graph, can we predict the diameter of the graph, right. So, that is another fundamental problem which people have addressed and attempted to solve, and there are different kinds of estimates on the diameter of the graph, right. So, we have to find out and appropriate this thing and this, but in many cases we actually have some expectation about the length of the plan. So, people can actually give some higher figure here and then be able to solve the problem. Okay. So, this we have already discussed: precondition axioms, action exclusion axioms, state constraints, etc. Right. So, with this we come to the end of the section on SATPlan, and we are also at the end of the chapter on planning. So, any questions?
In the planning graph, what was the exactly fixed point means?
Okay. Okay, let me, you want to know, your question is what is the fixed point that we were talking about when we talked about expanding the planning graph. Okay. It goes on like this, that we have an initial state set of literals, right, that is the initial state. So, this has a set of literals which are in conjunction. So, I can have some literal L1 and not of L2 and so on, right. These are all part of the initial state. Then when I apply actions, I want to apply the set of actions on this. Now, see, all actions here will not be applicable because their precondition will not be there in this. So, I can apply an axiom provided that the precondition of that axiom is there in this set. So, suppose that requires L1 and not L3, but you do not have not L3 here yet. So, you cannot apply that axiom. So, there is a subset of the axioms that you can apply now. When you do that, then you will get a new set of literals that are the effect of those actions. Also, each of these literals will get carried over to the next because of the persistence actions, right. So, whatever we have, all of them will get carried over, and in addition, because you are applying some actions, some new literals can get generated, right. Now, recall that you can, this set of literals can contain negations of different literals. For example, you can have L1 and you can also have not L1, right. But this L1 is generated by some action, this not L1 is generated by some other action. Those two actions are mutually exclusive, I cannot take both of them, but I can take either of them. So, in this set I am maintaining all possible literals that I could have generated, right. I cannot generate all of these at once, but I can generate any subset of that which is consistent, right. So, again on this literal set I can again apply the set of axioms, and now some of the actions which previously could not be applied may now become applicable because the literals which were missing have come in, right. So, again by applying this set of actions I will get another set of literals which is a superset of this, because all of these will get carried on by the persistence and some new ones can get added. So, in this way we continue, and the claim is that after a finite number of iterations you will find that in two successive iterations this set Sk and this set Sk plus 1 are the same. So, I will find that Sk is equal to Sk plus 1, and when do I say that these two are identical? If they have the same set of literals and they have the same set of mutex links, right. That is when I say that these two are identical. Then if I apply the set of actions again, I will get the same thing. So, this is the fixed point of the set of actions that I have, right. So, if up to that point of time also I have not been able to obtain the set of goals in a non-mutex manner, then I know that the plan does not exist.
So when the literals are same in both the sets, then automatically the links will be the same.
No, because what may happen is you can have two literals here, say L1 and L3, which are mutex, right. But when you apply the action once again, then from some other, suppose L2 and L1 were non-mutex, then you get L3 from L2, right. Suppose using these actions once again you get now L3 from L2, and because L1 and L2 are non-mutex, so now in this one L1 and L3 will be non-mutex, right. So, it is possible to have the same set of literals, but the number of mutexes can decrease. Right. Okay. There has been some debate on what kind of problems require what kind of planner. So, it is still not a problem which is well decided as such, but people have begun to understand that what are the kinds of problems can be tackled by which kinds of planners. And the general understanding is that if your planning problem is NP complete, then graph plan and SATPlan in general work better. Whereas, if your planning problem is solvable in polynomial time, then partial order planning usually finds the solution more quickly, because in SATPlan and graph plan adding out all those constraints themselves take a lot of time. To create the instance of the SAT takes a lot of time. So, for those problems which are polynomially solvable, it is usually the case that POP finds the solution much more quickly. The overheads do not balance out. But for hard problems, POP can take a very long time, because it will have to see after it has generated the graph, recall that you have to do extract solutions. Okay. It has been shown that the planning problem is P space complete. Do you know what is P space complete?
Can be solved by Turing machine polynomial space.
Yes.
Problem can be reduced to this problem.
Yes. Is this harder than NP complete? Well, if P is not equal to NP, then yes. To give you a very quick idea about what this is, see, okay, firstly we have a set of problems which are in NP, which means they can be solved by a non-deterministic polynomial time algorithm, right. And then there is a class called co-NP. these two differ in the sense that these are duals of the other problem. For example, if I ask you that given a formula CNF formula f, is it satisfiable, then if the answer is yes, it is satisfiable, you can give me a witness quite easily, right. How can you give me a witness? You will just give me an assignment to the variable values. But if the formula is unsatisfiable, then how will you prove it to me? How will you prove that the formula is unsatisfiable? It is not easy, right. So, for the yes answer, I have a polytime verifiable witness. For the no answer, I do not have any such thing. In the co-NP, it is the other way around. For the no answer, I have a polytime verifiable witness, right. Now, for example, if I ask is f valid, is it true for all instances, all instantiations? If the answer is no, then you can give me a counter example, but if the answer is yes, you can't do that. So, while satisfiability is in NP, unsatisfiability or validity is in co-NP, right, and we have P, the set of polytime solvable in the intersection of this, because we can for polytime solvable problems, the yes can also be proved in polynomial time, the no can also be proved in polynomial time, right. Now, then people said that okay, if I gave you an oracle which could solve NP problems in polynomial time, then what could you do? So, suppose somebody gave me an oracle which is a black box and can solve these problems in a jiffy, right. Then we can have problems which are hard to solve with that oracle. So, this is the higher class, right. So, we can build a similarly like NP and co-NP, we can build a similar class on top of this. So, this is the set of problems which can be solved using a non-deterministic polynomial time algorithm given an oracle which can solve NP problems in polynomial time, right, and this is the co version of that, the dual of that, right. So, in this way we can build a hierarchy. So, again we can have something on top of this like this, and we can have something on top of this like this, right. So, this is how the hierarchy builds up, and this hierarchy will build up forever. This whole class, this hierarchy is called the polynomial hierarchy, and this whole polynomial hierarchy can be solved in polynomial space, right. So, that is the class P space that we have, right. So, when we talk about P space complete, it means that it is harder than NP, harder than NP to the okay. So, it is harder than all these classes. So, the planning problem is known to be P space complete, but the generation of the graph up to the depth d can work in polynomial in the depth d, right. So, it is the extract solution part which is hard, right. The one that we totally glossed over is actually the hard problem, right. Once you have the set of goal propositions in non-mutex form, then extracting the solution is hard, right. So, because that is hard, so if your problem is NP complete in nature, then that part is really difficult to solve, right. So, algorithms like GraphPlan and SATPlan, which solve them as satisfiability problems, tend to work better for NP complete kind of problems. So, we are going to start a new topic from this lecture, and this topic is also a very important topic in AI. Namely, we will be studying reasoning under uncertainty. So, we have to brush up our school funda on probability. There will be quite a bit of probability coming up for you. So, let us get started. So, why do we need reasoning under uncertainty? So, let us see a few examples to get a clearer picture about why this is at all necessary. Firstly, the problem of handling uncertain knowledge. Suppose we are given the rule that for all P, symptom P toothache implies disease P cavity. So, this says that whenever one has a toothache, then that person has the disease which is a cavity in the tooth. Now, this is not correct because toothache can be caused in many other cases, right. So, we cannot say that whenever we have toothache it is because of cavity. So, if we have to actually analyze the case, the problem of toothache, then we have to comprehensively specify that what are the different causes for which this can happen. So, cavity is one, gum disease is one, impacted wisdom is one, and so many other cases for which we can have a toothache. Now, enumerating all of these is a problem because all of these may not be known, right, and you can miss out quite a few. Like for example, you can have toothache also if somebody has hit you on the teeth, which you would probably not put in this rule, right. But for a diagnostic system, unless you have the complete set of causes, then this rule will formally not be correct, right, because we are using implication here. Let us try to model this in the other direction. So, suppose we want to say that for all P, disease P cavity implies symptom P toothache. So, we are saying that whenever there is cavity, then the symptom is toothache, right. But this is not correct either because all cavities do not cause toothache. So, even if someone has a cavity, that person may not have a toothache. So, this is a kind of scenario which is very difficult to represent unless we use some kind of statement which says, okay, sometimes the cavity can cause toothache, and if we have toothache, then sometimes it is because of the cavity, right. Now, what are the reasons for using probability? One is that without using probability the specification becomes too large, as we were seeing. You have to explicitly enumerate. So, what we will do here is we will start breaking this up as follows. We will break this up as probability of J given A, right, and times probability of, okay, why J given A? Because if you recall in the belief network that we had here, slides please, in the belief network, slides please, in the belief network that we had here, slides please, in the belief network that we had here, we had J, only alarm was the predecessor of John calls. So, that is why for the probability of John calls, only given the alarm is what is relevant, okay. So, we have here Pj given A and then Pm, text please, given A because Mary calls given alarm, and then probability of A given not B and not E, and then times probability of not B and probability of not E. Right. So, it is the product of all these. So, what does this mean? This means that when I have a set of literals here, then the probability of the conjunction of this in the belief network is given by the probability of each of those events given the values of the predecessors of those in the belief network, right. Now, if some of these was missing, like if A was not there, then also we will have to bring this here and then reason about probability of A, right. So, if we just wanted to know about probability of J, for example, then we will have to first look at probability of J given A times probability of A. If you have 10 parents of X, then you have 2 to the power of 10 entries in the conditional probability table. So, if you have the ordering appropriately done, then you will find that the number of parents of X for every X will be limited, otherwise it will become very large. So, we will see in the next lecture that how we are able to deduce this to some extent.